Hello, welcome back to this channel. Today we're going to talk about the single phase power flow problem, and we're going to look at the second topic, which is power factor correction. And so today we're going to have two short video clips. Let's start with the single phase power flow problem. So as always, I'm going to put the Google Colab notes in the link in the description down below here. Let's start with the single phase power flow problem. We're gonna start with we're gonna focus on the example. So the concept of the power flow problem is instead of giving the source voltage, you're trying to find the power absorbed or delivered to the various elements in the circuit. Now we know the power absorbed or delivered to certain elements, and we're trying to find the voltage or the power at the source. So that's what this power flow problem entails. In the practical system, the power flow problem is very important because let's see, we have very complicated power system, really interconnected. There are many generators on the system, and how you determine how much each generator will supply the amount of power, right? So these are done by the power flow problem. So you solve the various loads and various nodes, which we call the buses, on the power system, and you're trying to figure out what would be the supply amount for each generation, for each generators. And so these are the very practical system, but also the power flow is useful in terms the planning process and how you're gonna build a new capacity at certain locations. So these are not just the academic exercise, but this is really practical in the real world. But in this course, we are looking at, of course, very simple system, right? This 200 level course, we're not gonna look at very complicated. You may consider a 400 level course in the power system, and if you decide doing in the power area. And so let's look at this simple example here. I have a single phase system. I have the source voltage Vs, and that supplies the power to the load impedance. The load impedance is not given, but it's given in terms of how much power this absorbs. So absorbed power 5 kilowatts. And the power factor of this load is 0.85. The lagging power factor, lagging means the Z sub L must be inductive, right? Because the lagging power factor means the current lags the voltage, and therefore the reactive power delivered to the load is positive, and the load is reactive or the inductive. And the voltage across the load here, we know the V sub L. The magnitude is 120 volts, and find the complex power supplied by the source, right? So there are, let's see the thinking process here, and also we want to find the voltage magnitude of the source. So once we find the voltage, the complex power by the source, and then the voltage will be easier, okay? And let's see, we're gonna use the principle of complex power conservation. And if we can find the QL, let's see if we can find the SL, which is PL plus JQL. And remember the P sub L, that's the real power, that's 5 kilowatts, right? Delivered to the load, and the QL would be the reactive power, Q sub L, that's reactive power delivered to the load. And if we can find these, and also we can find the S line, the complex power absorbed by the line, then we can find the complex power by the source, supplied by the source, and then the S sub S is going to be S sub line times plus S sub L, right? So a few things we need to find out, and remember one way we can find this is if we know the current. Let's see, call this I sub L, And the S sublime is we can figure out the current, this current magnitude times Z sub L, Z sublime. That's the one way to find the complex power. We have 3 different ways of finding complex power. If you're not comfortable with this, go back to the last lecture, which is quite a bit of time ago since we had this break here. And so we can, the things we need to find out is QL, right? Because the PL is already known, so we can find the QL is going to be equal to PL over the PF, the power factor, and this will give us the apparent power, right? And then the apparent power times the cosine, the power factor angle, which is square root of 1 minus PFL squared. Since this power factor is lagging, that means the QL is positive, right? We don't need to put a negative sign there. So if we have this, we got a 5,000 divided by 0.85, then times square root of 1 minus 0.85 square, and the number calculated beforehand, that's going to be 3.1 kilowatts, kVAR. Right, so that's for the this one is done, right? And then we need to find the S line. We only need to find the I sub L, and the I sub L is going to be equal to S sub L over. We only need to know the magnitude. We don't need to know the phase angle, and so this is going to be V sub L, right? So that's the apparent power equal to the magnitude of the current and times the magnitude of the voltage. And then we have the SL, that's going to be equal to PL squared plus QL squared, take the root, right, divided by VL, and VL is 120 divided by VL. Or you can find this SL using this one here, right? You can use the PF. That's also correct. If you don't want, alternatively, if you don't want risk the error you may make in the QL, so if you want to recalculate this, that's fine. Then times 1 over VL, and that's going to be equal 5,000 divided by 0.85. So this apparent power times 1 over 120, and the current is 49.02 amps in RMS value. And now we can find the S line, right? So the S line is going to be equal to I sub L, the magnitude square times Z line. And if you substitute the values, that's going to be 49.02 times the Z line. Z line is 0.1 plus 0.5 J, right? So this is the value we have here. And so therefore, that's going to be equal to, again, here I have the value calculated. That's 240.3 plus 1201 J. The unit for the complex power is volt amps, and therefore the SS is going to be equal S line plus S sub L, right? So that's the power supplied by the that's going to be equal 5.24 plus 4.30 J. This many kilo volt amps, kVA. Okay, so this is the value we find for the complex power, and now we need to find. So this is the first one here, and this is the first one, and the second one here is we need to find the VS magnitude, and since the VS. So since the SS magnitude is equal VS times the IL, right? So the IL, the load current, is also the current from the source. So therefore, we can find Vs by dividing these the apparent power SS by I sub L magnitude, right? So that's going to be equal 5.24 square plus 4.30 square. Take the root, so that's the magnitude, and times 1,000, that's the volt amps, and then divided by the 49.02, and the Vs I calculated, that's 138.3 volt RMS value. And the current, the voltage here is at the source is higher than the load voltage, right? So these are the simple example of how we do the power flow. And in the Google Colab notes, I framed this problem slightly different, and you can take a look how we solve it there. And by you can find the current first, and then you can find the source voltage. So this problem is the way of solving this problem definitely not unique. So I have these two methods laid out in the Google Colab notes. Take a look. And next, we're going to take a look at the power factor correction.